Hi, I'm Mr. Lai. Today we'll learn hydrogen bond, Dative bond, metallic bond. What is hydrogen bond? It is the attraction force between the hydrogen atom with the high electronegativity atom, such as nitrogen, oxygen, or fluorine. Electronegativity means the higher tendency of the atom to attract electron towards itself. So oxygen has the high electronegativity. So oxygen with the hydrogen atom, there will be the bond we call hydrogen bond forming. Let us watch the video.
What are hydrogen bonds?
Hydrogen bond form.
An attractive force called a hydrogen bond can exist between certain molecules. These bonds are weaker than ionic or covalent bonds because it takes less energy to break these types of bonds. However, a large number of these bonds going on can exert a strong force. Hydrogen bonds are the result of an unequal charge distribution on a molecule. These molecules are said to be polar. If we look at a water molecule, we can see the oxygen atom shares electrons with two different hydrogen atoms. So, in total, this molecule has 10 protons, 8 from oxygen and 1 each from the hydrogen atoms, and a total of 10 electrons, 2 shared between the oxygen atom and hydrogen atom number 1, and 2 shared between the oxygen atom and hydrogen atom number 2, and the other 6 non-shared electrons from the oxygen atom. So, this water molecule is electrically neutral, but it has a partial positive side, the hydrogen side, and a partial negative side, the oxygen side of the molecule. The electrons are not shared equally within the molecule, as they have a higher probability of being found closer to the nucleus of the oxygen atom, giving that end a slightly negative charge. So the hydrogen atom's end of the molecule will have a slightly positive charge. These charged ends weakly attach the positive end of one water molecule to the negative end of an adjacent water molecule. When water is in liquid form, there are a few hydrogen bonds. Solid form, many hydrogen bonds, and when water is steam or gas, there are no bonds because the molecules are too far apart to form any bonds. Hydrogen bonds only form between hydrogen atoms that are covalently bonded to an oxygen, nitrogen, or fluorine atom. Hydrogen bonds are also important in the structure of proteins and nucleic acids, which we will cover in later videos. So now we know that water molecules are polar, or have a slightly positive and slightly negative end. And in fact, many lipids, or fats and oils, are not polar, so their molecules share electrons equally in their bonds. So these are non-polar molecules. This means that when water and oil come together, they do not form bonds with one another. Even when we try to mix them, the water molecules will eventually separate because their polar molecules are attracted to one another and will form hydrogen bonds, which will separate the water and the nonpolar oil molecules. And that be the basics on hydrogen bonds.
What is the role of the hydrogen bonds in daily life? Example, when you take bath, your wet hair will stick together. The plant carry out the capillary action. That means the water absorbed from the roots going up to the leaf part. The forming of the secondary and tertiary protein. The form ice structures. So I will show you how can the reptiles or the small insect walk on this water surface.
This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight.
And why does the ice float in the water?
Why do these ice cubes float? If these were cubes of solid argon in a cup of liquid argon, they would sink, and the same goes for most other substances. But solid water, aka ice, is somehow less dense than liquid water. How's that possible? You already know that every water molecule is made up of 2 hydrogen atoms bonded to 1 oxygen atom. Let's look at a few of the molecules in a drop of water, and let's say the temperature is 25 degrees Celsius. The molecules are bending, stretching, spinning, and moving through space. Now, let's lower the temperature, which will reduce the amount of kinetic energy each of these molecules has. So they'll bend, stretch, spin, and move less. And that means that on average, they'll take up less space. Now you'd think that as the liquid water starts to freeze, the molecules would just pack together more and more closely. But that's not what happens. Water has a special kind of interaction between molecules that most other substances don't have, and it's called a hydrogen bond. Now remember that in a covalent bond, 2 electrons are shared, usually unequally, between atoms. In a hydrogen bond, a hydrogen atom is shared, also unequally, between atoms. 1 hydrogen bond looks like this. 2 look like this. Here's 3, and 4, and 5, 6, 7, 8, 9, 10, 11, 12. I could go on. In a single drop of water, hydrogen bonds form extended networks between hundreds, thousands, millions, billions, trillions of molecules, and these bonds are constantly breaking and reforming. Now back to our water as it cools down. Above 4 degrees Celsius, the kinetic energy of the water molecules keeps their interactions with each other short. Hydrogen bonds form and break like high school relationships. That is to say, quickly. But below 4 degrees, the kinetic energy of the water molecules starts to fall below the energy of the hydrogen bonds. So hydrogen bonds form much more frequently than they break, and beautiful structures start to emerge from the chaos. This is what solid water, ice, looks like on the molecular level. Notice that the ordered hexagonal structure is less dense than the disordered structure of liquid water. And you know that if an object is less dense than the fluid it's in, it will float. So ice floats on water. So what? Well, let's consider a world without floating ice. The coldest part of the ocean would be the pitch-black ocean floor, once frozen, always frozen.
All these phenomena occur because of the hydrogen bonds. Why the ethanol able to soluble in water? Because of the formation of the hydrogen bonds between the ethanol molecule. As you can see, ethanol molecule consists of the oxygen atom. The oxygen atom will form the hydrogen bond with the molecule, with the water molecule. So, because of the hydrogen bonds, an ethanol able to soluble in the water. Practice 5.4. Meaning of the hydrogen bonds. Hydrogen fluoride exists as a liquid at room temperature. Explain how it formed the hydrogen bond. Can the hydrogen bond form among hydrogen chloride molecule? Why the papers stick together when wet? So, the keywords I already highlighted with the yellow color. You can see hydrogen bond is the attraction force between the hydrogen atom with the highly electronegativity atoms. Hydrogen fluoride molecule consists of the fluorine, which is higher electronegativity. So the attraction force between the hydrogen atom and the fluorine atom will cause hydrogen fluoride form, and the strong hydrogen bond is formed. So we need more heat energy to overcome the attractive force. As a result, the boiling point will be increased. So the hydrogen fluoride will be a liquid at the room temperature, but not a gas. Can the hydrogen chloride molecule form hydrogen bond? The answer is no, because the chlorine atom has the largest size compared with the fluorine atom. Why the paper will stick together, can split easily when we get some water in our finger, because the cellulose in the paper consists of the oxygen atom. It can form hydrogen bond when our hand, our finger is touched with the water. So it can be stick together easily. And what is a dative bond? It is the covalent bond between the two elements where one of the atom provide both electrons. I want to emphasize both electrons that form the bond. As you can see, nitrogen, we have the ammonium compound. So ammonium compound have 3 hydrogen, form the covalent bond with the nitrogen atom in the center. You can see. So here we have the lone pair, so without sharing. So now when one hydrogen ions is going to the ammonia molecule, ammonia compound, this lone pair will share to the hydrogen ions. So this bond we call dative bond is forming. Another example with the hydroxonium ion. Hydroxonium ion, when the H2O water molecule form a dative bond with the hydrogen ions. As you can see, the water molecule have the lone pair of the electron here. So when one hydrogen ions, positive ion, go near to the water molecule, the lone pair of the electron will share to the hydrogen atom. So this will form a dative covalent bond. When you want to draw the symbol of the dative bond, you can use an arrow to represent both of the electrons from the oxygen atom is shared to the hydrogen ions. Practice 5.5, explain dative bond. Explain the formation of the dative bond between ammonia. And the number 3, boron trifluoride has not achieved the octet electron arrangement because it has only 6 valence electrons. Can the boron atom form dative bond with the nitrogen atom? Explain your answer. So I will already highlight the answer with the yellow color. So dative bond is the share of the pair of the electron from the one atom only. Okay, so number 3, this one I want to highlight, can. Okay, because the ammonia has a pair of the electron which can share to the boron atom, and this bond we call dative bond. What is metallic bond? It is the electrostatic attraction force between the sea of the electron and the positively charged metal ions. The valence electron will detach from the metal atom and free to move through the metal. This will result in a sea of the electron. That means a lot of the electron they can move freely. Or we can call this a big pool of the delocalized valence electron.
Bond to nonmetals through ionic bonding, and that nonmetals bond to other nonmetals through covalent bonding. Now we turn to how metals bond to other metals, which we call metallic bonding. If we think of a solid metal, it basically consists of a giant structure of atoms that are arranged in a regular pattern. In this picture, we've shown each atom surrounded by the electrons in its outermost shell. When all these atoms are together in a metal though, they actually give up these outer shell electrons and share them with all the other atoms in the metal. This means that the atoms will all become positive ions because they've lost negative electrons. And because those electrons are now free to move about, we call them delocalized electrons. So there will now be loads of strong electrostatic attraction between the positive ions and the negative electrons. And it's these forces of attraction which hold everything together in a regular structure. So we call this metallic bonding. This gives the overall metal strength, and means that most metallic structures have high melting and boiling points, so are solid at room temperature. They are also good conductors of electricity and heat, because the delocalized electrons can carry electrical current and thermal energy throughout the structure. Another important property is that metals are malleable, which means that they can easily be bent or hammered into shapes, for example into thin sheets. This can be a bit confusing because we think of metals as being strong, and in many ways they are. But the fact that metals have such a regular structure means that the different layers can slide over one another. So they're not quite as fixed as you might have thought.
The question asks, is a matter made up of the atoms or ions? The answer is atoms. As you can see, even though the electron can move around from the atoms, some atoms may don't have any electron, but it doesn't mean it don't have the electron, because it's still there in the structure. So we cannot say the matter is the ions, but they are made up of the atoms. Electrons always move freely in the metal structure, which carry the charge from negative terminal to the positive terminal when the electricity is supplied. So you can see from negative to positive terminal. Practice 5.6, meaning of the delocalized electron. How the metallic bond is formed in metals. Give the example of aluminium, explain how it can conduct electricity. So, delocalized electron means the mobile electrons that are not owned by any atom or ions. And explain the metallic bonds. You can say the delocalized valence electron can move freely in the metal to form electron C, and the electrostatic attraction force between the electron C and the positively charged metal ion will form metallic bond. And aluminium metal, because it has the delocalized electron which can move freely and carry the charge from negative terminal to the positive terminal, so it can conduct electricity. So let us summarize of the hydrogen, Dative, and the metallic bonds.
The permanent dipole in a covalent bond between a hydrogen atom and a fluorine, oxygen, or nitrogen atom is
particularly strong. Thus, the attraction between the electron deficient H delta positive of one molecule and the lone pair of electrons on a fluorine, oxygen, or nitrogen atom.
The permanent dipole in a covalent bond between a hydrogen atom and a fluorine, oxygen, or nitrogen atom is particularly strong. Thus, the attraction between the electron deficient H delta positive of one molecule and the lone pair of electrons on a fluorine, oxygen, or nitrogen atom of another molecule is much stronger than the permanent dipole-dipole attraction mentioned before between the two hydrogen chloride molecules. This particular type of dipole-dipole attraction between the electron deficient H delta positive of one molecule and the lone pair of electrons on a fluorine, oxygen, or nitrogen atom of another molecule is given the special name of hydrogen bond. So, A hydrogen bond is the attraction between the H delta positive of one molecule and the delta negative on the lone pair of a fluorine, oxygen or nitrogen atom of a neighbouring molecule. Even though a hydrogen bond has only about 5% the strength of a covalent bond, it does have a significant effect on the physical properties of compounds. For example, were it not for hydrogen bonds, both water and alcohol would be gases at room temperature and pressure.
Now we look at the dative bond, also known as coordinate bond. Dative bond actually is referred to covalent bond, where the electron pair that is shared comes from the one atom on it. Examples 1. Oxygen atom achieves octet electron arrangement and hydrogen atom achieves stable duplet electron arrangement in the water molecule. Hydrogen ions does not have any electrons in the shells. The lone pair of the electrons that are not involved in the covalent bond in the water molecules will be shared with the hydrogen ions through the formation of dative bond. In the hydroxonium ions, oxygen atom and all the hydrogen atoms have achieved stable octet and duplet electron arrangement respectively. So in this case, the oxygen atom becomes the donor and hydrogen ions becomes the acceptor. Example 2, we talk about the ammonia. In the ammonia, nitrogen atom achieve octet electron arrangement and hydrogen atom achieves stable duplet electron arrangement in the ammonia molecule. Hydrogen ions does not have any electrons in the shell. The lone pair of electrons that are not involved in the covalent bond in the ammonia molecule will be shared with hydrogen ions through the formation of dative bond. In the ammonium ions, nitrogen atom and all the hydrogen atom have achieved stable octet and duplet electron arrangement respectively. Ammonia is the donor and the hydrogen ions is the acceptor.
Metals are malleable. This means that they can be molded into different shapes. Metals are very ductile. This means that they can be stretched into wires. To fully understand these properties of metals, we must understand metallic bonding. When we talk about metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the free-floating electrons around them. Since these electrons are free to move around, the term sea of electrons is also used. What is a lattice structure, and where have you heard this term before? The term lattice structure means that there is a regular repeating pattern. We have heard this term before when discussing ionic lattices. It is used to describe the alternating positions of the metal and non-metal ions. In metallic structures, however, there are only metal ions. These metal ions are arranged side by side in a regular repeating pattern.